This is the first of 2 videos on solids, liquids, and gases. Hopefully you have your notes printed out so that you can fill it in and follow along. So the first thing, just looking at solids and liquids and gases, let's just look at structurally what do they look like. Well, a solid, what makes them a solid is that the particles that make up a solid, they're very close together, and because they're so close together, what happens is that if you take these particles, right, this particle, let's say we add in another one, the thing that makes it solid is that they're so closely spaced that this red particle, if that's part of our solid, it can't move around within this solid because they're so closely spaced. The other thing you need to know about these particles is they are moving, but what they're doing is they're just vibrating back and forth, and all of them are vibrating back and forth. So there is some movement, right? If I can grab it, if this is our particle we're focusing on again, it's vibrating, it's just not moving around the solid. It's just kind of sitting there going back and forth, back and forth, back and forth. A liquid, well, in the liquid, there's a defined volume, right? It's only going to take up a certain amount of space, but these particles, they're spaced out a little bit more, and because they're spaced out a little bit more, it allows them all to move around, where now this particle can move and this one's moving, and so now they're able to move within that substance because of the spacing of the particles. So because these are allowed to move, the shape of the liquid can change, right? It can spread out or it can take the shape of a container because these particles can move around and kind of take up a different space, right? It has a definite volume. The amount of volume it has isn't going to change, but they are moving, and they're moving each a little bit faster, right, than the solids, which are only vibrating back and forth. And then you have a gas. Well, a gas, these particles are going to be spaced very far apart, and they're going to be moving very, very quickly all over the place. And so as this particle moves around, it's going to stay in this container, right, if it's a sealed container, but all of these particles are going to spread out so that they take up the whole entire volume of the container. So you can see the spacing is different, right? That the solids are a defined shape, they're vibrating back and forth. Liquids are a certain volume but can move, the particles can move past each other, and then gases are going to spread out and expand, and they're moving faster than all the other particles. So down to the next part. Are they compressible? Right? Well, gases, yes, there's a high compressibility there. You can definitely take a gas and squeeze it into a smaller volume. A liquid, basically, it's no, but you can slightly compress them, and solids are the same thing. Technically, you can slightly compress them, but you're going to consider essentially both of these a no if it was on a test. Density, just ranking them in differences of density, right? You can see that the solid, the particles are close together. Liquids, they're a little bit further apart, and then gases, they're even further apart, which means that as far as the density goes, this is the highest density, right? This is the medium or the middle of the road, and this is going to, sorry, did I switch that? I switched that around. Right, these are spaced out the furthest, so they have the lowest density, and this has the highest density, right? They're more closely spaced. Okay, ability to fill its container. Gases are going to expand or compress to completely fill the container. And both of these here they're not going to expand at all. They're going to stay a definite volume. Number 4, ability to take the shape of the container. Right, gases can, liquids can, as I was explaining, but solids are a definite shape. They're not going to change and take the shape of the container. And the last one, rate of diffusion, and diffusion is simply how those particles spread out or how that substance spreads out, right? Gases are going to have a high rate of diffusion. You know, if you were to have a candle burning or a flame burning and it was releasing smoke in a room, those smoke particles, right, those gas particles would spread out very quickly and start spreading throughout the room, right? Liquids, yeah, they spread out, right? They're going to spread out on the floor. You fill it in a container, they spread out, but really they're changing shape, but they're really not spreading out that much at all. And solids are basically no, right? These are the lowest. They're not going to spread out at all. So really only the gases are diffusing. Okay, moving on to property of liquids. Okay, viscosity. So let's define that term. Viscosity is the resistance to motion that exists between molecules when they move past each other. So basically what that's saying, right, is that when I was up here and I was talking about how these particles can move around, how easily can they move around? Right, if you have liquid water, well, the particles can move past each other very, very easily. If you talk about syrup, well, syrup's a liquid, right? A liquid that is going to take the shape of the container, but now it's harder for these particles to move past each other, so it has a higher viscosity because of that. So examples, right? High viscosity would be, let's say, magma, right? Lava. Honey, I said. Syrup would be another example. Those are all where it's a really thick, kind of think of a thick fluid that doesn't move past each other very easily. You could almost say peanut butter could be a liquid, right? It's going to take the shape of its container, but it has a very, very high viscosity. It doesn't move very easily, or think of it again as a thick substance. So low viscosity, right? Water spreads out very easily. You could take, right? Kool-Aid is kind of almost like water. It's a little different, but it spreads out very equally. Rubbing alcohol is another one. Windex, any sort of liquid like that that spreads out easily. Okay, let's move to the next page. Okay, what is the cause of viscosity? Well, you, in your previous assignment, had looked at intermolecular forces. Well, these intermolecular forces are the reason why you have substances with different viscosities. And instead of writing intermolecular forces all the time, feel free to write IMF for intermolecular forces to represent them. So just quick, right, what is intermolecular forces? They are the attraction, right, between molecules. So they're not intermolecular forces, right, they're intermolecular forces. So if you have a oxygen particle, right, and another oxygen particle and a hydrogen particle, right? The attraction of the hydrogen to the oxygen, that is the intramolecular forces, right? Because two oxygens and a hydrogen are going to make up a molecule, and this molecule is going to be attracted to another molecule. This attraction from one molecule to the next molecule, that's the intermolecular forces. Okay, so the stronger the attraction of those forces, the higher viscosity that the substance is going to have. Okay, the other thing that viscosity depends on is, right, temperature. If you take lava, really, really hot lava has a much lower viscosity. If you take, you know, let's say it was the peanut butter. If you heat up peanut butter, it's going to have a lower viscosity. So the higher the temperature, right, the lower the viscosity is going to be. So obviously the opposite, right? The lower the temperature, the higher the viscosity. Okay, next section here, surface tension. So we have surface tension, right? Kind of a generic definition here. It's the skin that forms at the top of a liquid because of the intermolecular forces. So what exactly does that mean? So what happens is you have these particles that make up a liquid, right? And these particles are moving around. Well, if they're moving around all over the place within the liquid, right, and they're constantly moving around, what's happening at the surface is there's these other, right, molecules that are making up the surface, making up the substance, and they're at the surface. And because there's an attraction between those particles, when this particle is bouncing around, it gets up to here and it can't go through because of the skin that forms at the top, right? Because there's these intermolecular forces, it can move around within the substance, it just can't break free from the substance. So it's stuck in the substance. The only way that you can break free from that surface, right? If these are all moving around at random velocities, the only way that it could break free is if, again, you have these particles, right? And at the top, it's forming this skin because of the intermolecular forces. If the particles that are within that substance, right? If this thing is moving real fast and it's, right, going crazy, then it can break free and break through that skin and essentially evaporate, right? It's in a liquid, it's in a liquid form, and if it can break free, now it's out into here floating around, which means it's now making up the gas that's in the room that's outside of this container. So that evaporation, right, which is really called vaporization, and this really is the word that you should use whenever you're talking about a liquid going to a gas. You should use vaporization, not evaporation. But it's the process of, right, a liquid becoming a gas. And I was just showing you right up here that if this particle gets enough energy, if it's moving fast enough, it can break free. And that's what happens when you boil water, right? When you boil water, there's this hot surface down here that's heating up. And when this particle gets down here, it gets some of that energy from heating up, and boom, it can break free because it's moving so much faster because it got hot. And as it got hot from the surface, that means it essentially moved faster. Okay, something to keep in mind, as I was showing from that example above, right, that not every particle, even though a substance has the same temperature, it doesn't mean that every particle is moving the same speed. So we're going to look at these particles in this liquid here, and we're going to say right? That there are particles that are moving slow, they're moving medium speed, and they're moving fast. And that's realistically what's happening. Some particles are moving faster than others. So the faster moving particles that make their way to the top of the surface, right, which would be this one, it's moving real fast. This one's kind of moving medium, right, and this one's moving real slow. This fast moving particle at the top will evaporate, right, or will vaporize because the molecule has more kinetic energy. And if you remember from your previous classes in junior high, kinetic energy is simply the energy of motion, right? If it has more energy, basically it's saying it's moving faster. And so it has more kinetic energy than the average molecule. So this fast moving molecule can, like I said, oops, can't spell. Like I said earlier, it can break through that surface tension or that skin from the intermolecular forces and break free into a gas, right? So the effects of temperature on evaporation, right? High temperature makes, as I said, the molecules move faster, and because they're moving faster, that means they're able to break free, so more particles are going to evaporate. The thing you need to realize is, even at room temperature, this is happening, right? You have water sitting at room temperature. The only difference is at room temperature, there's not very many particles that are moving fast. Most of them are in here, and so they're not breaking free. But there is going to be some that are moving fast, and as a result, they will break free and you get evaporation. So last thing for this video, volatile liquids. These are liquids that evaporate very easily, right? And why would they evaporate easy? Remember, in order for this particle to break free, it has to get through these intermolecular forces. Well, how's it going to get through these? What would make it what would make it a volatile liquid? Well, if these intermolecular forces are weak, it would be easy to break through and evaporate. And that's what it is. Volatile liquids evaporate easy because of weak intermolecular forces. So that is the end of video 1. Video 2 should be about the same length, so make sure you have about the same amount of time to sit down and take some notes.